Webb has already shattered our models of the early universe. Now it's looking closer, at the stellar nurseries of our own galaxy, and at the atmospheres of worlds orbiting other stars. This is what it found when it looked for life. In Part 1, Webb found galaxies too old for our theories, too massive, too bright. It broke the models we used to describe the early universe. Now it turns closer, to the stellar nurseries where new stars are being born right now, to the atmospheres of worlds orbiting other suns, to a question that has haunted science for centuries. Are we alone? For the first time in history, we have a machine that can actually look for the answer. Turn Webb away from the distant universe and point it at something closer, a star-forming nebula in our own galaxy. And it shows you something just as staggering. This is the Carina Nebula. It's 8,500 light-years from Earth. And this ridge of gas and dust, the cosmic cliffs, is where stars are being born right now. Not metaphorically. Actually right now, in geological time. Every bright jet you see punching through the nebula is a newborn star, a protostar blasting out plasma as it collapses. These stars are weeks to thousands of years old. Infants, cosmically speaking. Hubble saw the tops of the cliffs. Webb sees into them, through the dust, into the stellar nursery beneath. Then there's the Tarantula Nebula, the largest and most active star-forming region in our local group of galaxies, 170,000 light-years away in the Large Magellanic Cloud. Webb found over 800,000 previously uncatalogued stars in a single observation. Hundreds of thousands of stars we simply didn't know existed. We've been studying the Tarantula Nebula for decades with other telescopes. Webb effectively revealed it for the first time. One of Webb's most transformative capabilities has nothing to do with distant galaxies. It's about planets orbiting other stars, and whether any of them might have air we'd recognize. The technique is called transmission spectroscopy. When an exoplanet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere before reaching us. Different molecules in that atmosphere absorb specific wavelengths of light, like fingerprints. Analyze the spectrum, and you can identify the chemicals in an alien atmosphere from hundreds of light years away without ever going there. Hubble could do this crudely. Webb can do it with surgical precision. In 2023, Webb pointed at K2-18b, a planet 2.5 times Earth's radius, orbiting in its star's habitable zone, 120 light-years away. The spectrum came back with carbon dioxide, methane, and a tentative signal of dimethyl sulfide, a molecule that, on Earth, is produced almost exclusively by living organisms. Almost. Scientists are careful to say, this is not evidence of life. The signal is weak. It needs confirmation. But it is exactly the kind of biosignature we built Webb to look for. For the first time in history, we have a machine capable of asking the question. Webb's first exoplanet target, announced on that original day, one release, was WASP-39b, a hot Jupiter 700 light-years away, a planet half Jupiter's mass, orbiting its star in just 4 Earth days. Surface temperature, 900 degrees Celsius. Nothing like Earth. Nothing like anything we'd want to visit. And yet, what Webb found there was a landmark in the history of science. Carbon dioxide detected definitively. First direct CO2 detection ever made in an exoplanet atmosphere. Water vapor, sodium, potassium, carbon monoxide, and most surprising, sulfur dioxide, a molecule produced when sunlight drives chemical reactions in the upper atmosphere. We had theorized that photochemistry happens in exoplanet atmospheres. Webb confirmed it. In the first data set, before Webb, the best atmospheric characterizations of exoplanets contained 1 or 2 detected molecules. WASP-39b gave us 6, in a single observation. What this means in practice: we can now build real atmospheric models of alien planets, understand their chemistry, their weather, their energy cycles. WASP 39b is a gas giant we could never live on, but it proved the method works. Every rocky planet in a habitable zone is now a viable target. Here's the thing about Webb that most people don't realize. It launched with enough fuel for 20 years of operation. Because the Ariane 5 rocket was so precise, Webb barely had to use its onboard thrusters to correct its trajectory. The original design lifetime was 10 years. The actual lifetime is now estimated at over 20. That's 20 years of looking, and the biggest questions are still unanswered. The first stars, Dal, population 3 stars, Iniaki stars, have never been observed. They formed before there were any heavy elements, burned fast and bright, and seeded the universe with everything heavier than helium. Webb might see their indirect signatures in the most distant galaxy spectra. Planet formation is happening right now around other stars, in disks of gas and dust, protoplanetary disks. Webb is mapping them in detail we've never had, watching planets assemble in real time. And somewhere, in one of the thousands of exoplanet atmospheres Webb will analyze over the next 2 decades, there may be a signal that cannot be explained by chemistry alone. A combination of gases that can only coexist if something is producing them. We don't know if that signal is out there. We don't know if life is common or vanishingly rare. But for the first time in the history of science, we have a machine capable of finding out. It's already out there. It's already looking. James Webb is the most powerful eye humanity has ever opened on the cosmos. It's rewriting our history of the universe, mapping alien skies, and hunting for the chemical signatures of life. And it has 20 years of fuel left. Whatever it finds next, we'll be watching.